Hello, everyone, and welcome to my talk. Thank you very much to the organizers for inviting me to present my work at the Perception, Action, and Learning workshop at ICRA. So today I want to talk about perceiving and acting in dynamic environments. And I typically work with manipulation robots. And for those of you who have not worked with manipulation robots, I can tell you they're pretty clumsy still. And they're especially clumsy in dynamic and uncertain environments, as illustrated in this video. Well, actually, in this video, it's not illustrated that they are clumsy. So anyway, this is Apollo. And Jim Mainprice here is kind of giving Apollo a hard time by changing the environment, while Apollo really has to be careful to knock anything over. It eventually succeeds, but what it requires to do that is actually a real-time perception system that can continuously perceive the environment, and a motion generation system or decision-making system that can take this feedback as input and actually react to it in real time. So such a system is really hard to build. And here is an overview, a very simplified overview of how the system looks like. You see in purple, the robot and the world. In green, you have all the modules that are responsible for the real-time perception. And in red, you have the reactive motion generation and decision-making systems, essentially. So each of these boxes actually has some contribution or makes a contribution to the respective subfield within robotics. But I don't want to talk too much today actually about what is in these systems. What I want to impress on you instead is that what is important is not only what is in these boxes, but also how you connect them together. If you take the same components and connect them in the wrong way, your system won't work. So what we did here in the system to enable the performance that you've seen in the video is to actually create a set of interlocked perception action loops that have very different frequencies. So to illustrate this, I'm going to show you very roughly how one time step in the system actually looks like. So the input to the system is basically raw sensory data, and that is depth and RGB data on the one hand, but also joint torques and joint angles that are coming into the system at 1 kilohertz. We use a real-time perception system to process this raw sensory data and to actually provide an occupancy grid map, a pose of the target object, and also a pose of the robot arm. Then this feedback that uses vision to basically uses this representation to produce a force field. And the controllers compute the next best action that bring the hand closer to the target object, here this drill, and at the same time push or lead the end effector away from any obstacles. And then this controller runs at a kilohertz, but at a much slower rate, at 5 to 10 hertz. We have an online trajectory optimizer that optimizes action over a time horizon of 2 seconds, and that relies on a feed-forward model. And it produces acceleration policies that are tracked with an inverse dynamics controller. So the latter, this online trajectory optimizer, is much slower and is only updated at 200 hertz. And it's fused with this feedback force field that is updated faster and can take changes immediately into account. So this is really how one time step in the system looks like. And we wanted to, in this particular paper that you've already seen at the bottom, to evaluate how important really the system architecture is. And we have done many different, we've run basically many different experiments in these 4 different scenarios. And 3 of those scenarios are dynamic. And I will, in the interest of time, just show you one of them. And that particular task is a pick and place task in a dynamic environment. What will happen is that you basically see Apollo again picking up the Pringles box, and Franziska Meyer here is going to push an obstacle in the way, and Apollo has to react to it. At the bottom of this, at the bottom right, you see what the robot sees. So the occupancy grid map, the pose of the hand, and of the target object. So now we did compare 3 different architectures where you see a classic sense plan act method and a local reactive feedback method that basically is Osama Khatib style, and then our proposed approach. And you see kind of what's happening here with these different approaches. The right one basically collides with the obstacle because it plans once and then just executes open loop. The middle one gets stuck at the obstacles and cannot really escape this local minima, but recovers when the obstacles are removed again. And the rightmost solution or system architecture can actually react and search for a solution and escape this local minima by using this online trajectory optimizer. All right. So this was about how the system actually looks like as a final result. And I hope I convinced you that it's important to put the different components together in the right way. And since this workshop is on sensing and action, I wanted to specifically talk about the methods that we use to actually enable real-time perception that provides a continuous feedback on the object pose, the robot pose, and the environment, so that the robot can make the right decisions. Okay, so what do these methods do? They basically take the raw sensory data and convert it to feedback for the robot decision maker. And basically what we have here is, first of all, an object tracker that is a model-based one. It takes as input a depth image and a mesh model of the object, and then outputs the 6D object pose. So here on the right, you see Jan Isak actually playing around with this. And you can also see how robust this pose tracker is to occlusions and to even taking this model of the object apart. Okay? And all of this is in real time. This is not sped up or anything. So just to give you an impression, this under the hood, this object tracker is essentially a particle filter. But the magic sauce here is that we're not only modeling the 6D pose of the object, but we're also explicitly modeling occlusions in the visual, in the space of the image. And in order to make that tractable, we basically had to implement a smart factorization that resulted in a raw black-Weiss filter, and all of this is implemented on the GPU. And if you are interested in trying this object tracker, maybe you need one for your manipulation robot, go to GitHub and check out this open source code, and you will be able to use this model-based object tracker. So apart from the object tracker, we also needed to track the robot, the pose of the robot arm and hand relative to the cameras in order to do accurate perception. So what you see here again is basically an extension of our object tracker to include the high dimensional system of, or to be able to track the high dimensional system of the 7 degree of freedom robot arm. And what we take as input is the depth image, but also the joint angles of the arm that, by the way, come in at kilohertz. And the output are estimated joint angles and biases. So, of course, we could only use the forward kinematics, but as we show here, on the top, you see actually that these forward kinematics are quite wrong. There's like multiple centimeters of error, really. And if you wanted to do any kind of fine manipulation, that's really not very helpful. And on the bottom, you basically see in comparison the output of this tracker. So this paper won the Best Paper Award in 2017 from RAL. So please feel free, go ahead and check it out. Here are some more examples of how the object tracker and the arm tracker actually work together in the real system. You also see basically the updated occupancy grid map that runs approximately, I believe, at 15 hertz. And you can also see that the object is sometimes even out of view. It suddenly falls over. There are lots of occlusions. So this tracker was really robust. So if you're interested, please feel free and check out this project. The code is actually really well written. All right, so I hope I impressed on you how important the tight connection is between perception and action, especially at multiple time scales. And we proposed this particular system architecture of interlocked perception action loops that run at different time scales. And through the system, we can achieve the kind of behavior that you see here, where the robot is really reacting immediately to changes in the environment. So one thing, though, that I want to guide your attention to is that the task, the high-level plan of actually bringing the Pringles box from one side to the other, this is not something that the robot came up by itself, right? This is a task that we, as the engineers of the system, have actually provided it with. And so we basically provided it with the underlying state machine that it is running here. And for each task, we essentially had a different manually designed state machine. So in our in more recent work that I've recently done with my student Toki, we actually explored how we can even add another layer for symbolic task planning on top of the motion planning, while maintaining this ability of the robot to be adaptive even in the face of a dynamic environment. Okay, so here's an example of how this looks like, right? So let's say the goal of this robot is to put the small box onto the large box, onto the shelf, basically. But the problem is that the small box is really outside of the workspace of this robot. So in order to figure out like how to still essentially solve this task, we are combining symbolic and geometric reasoning so that the robot can figure out, oh, I can just grasp this hook, pull the little box closer, and then finally reach it and place it on that shelf. So that is a solution or an approach that we were not the first ones to have. Other people have, of course, provided solutions to this, and I will specifically talk in more detail about a solution that Marc Toussaint et al. Have proposed in 2018. So what we specifically were interested in, again, was to develop plans that are really adaptive to moving targets and to a moving environment, right? And we were wondering, like, okay, let's say all these targets are moving. Like, how can the robot quickly and in real time actually adapt this symbolic plan or its motion trajectories, just like with Apollo before? All right, so this was our goal. And we adopted the approach that was proposed by Marc Toussaint et al. In 2018 on logic geometric programming. So what that does is basically combining symbolic and geometric reasoning. Essentially, a logic planner is combined with a motion optimizer. And really on the top, what you find is basically a trajectory optimization problem where H here is the terminal cost, X is the state, and G is the trajectory cost, using the continuous state X and the continuous action U as input, right? And we want to find a solution, or the robot should find a solution that minimizes this cost. So what is special about this logic geometric programming is that it adds a bunch of constraints that adhere to the logic plan that is basically output by, for example, a logic planner. So first we have a continuous F path here. So this basically the plan that is minimum has to still adhere to the continuous system dynamics, which change depending on the discrete state S. And then we have F switch, another constraint that describes the instantaneous system dynamics when a discrete action, AK, changes. And finally, this entire plan also has to adhere to an action skeleton that is produced by logic planning, right? Which basically describes successor states. All right, so basically as a logic planner, we just use strips planning. And here is basically a description of this planning problem, which has a bunch of propositions, actions with preconditions and postconditions, objects, initial state and goal state. And all of this we basically hand defined, at least these primitives. And then we can use these to use just tree search to find a logically coherent plan. All right, so now let's say we found this plan, basically a sequence of discrete states and actions. We still want to figure out, like, okay, is this plan actually possible for the robot to do? Can it have a continuous motion that can fulfill this plan and still be with, like, follow the dynamics of the arm and the joint limits and all of these things? And basically, Marc Toussaint and co-authors, they have formulated this optimization problem in the way that I've already shown you. And specifically, they sum the trajectory cost across all time steps that results in abundant Hessian that can be inverted efficiently with Gauss-Newton methods. And I want to also emphasize that the minimization is actually over a joint space trajectory. So you see the Q here, these are actually joints. Also the constraints function, you see that they are actually depending on the entire trajectory. And this coupling makes the Jacobian of the constraint function pretty complex. And the problem with the joint angles is actually that it is whatever joint trajectory is basically output, once you have this optimization problem solved, becomes invalid as soon as the environment changes and you have to run this entire optimization again. So how do we have a way to combine a symbolic plan with a trajectory optimization plan that is actually adaptive in case the environment changes? That was the question we were asking. And what we propose is really to reformulate the problem of finding such a plan from optimizing in joint space to actually optimize over relative Cartesian frames. Okay, so what does that mean? So, for example, let's say you want to pick up the small box and want to put it on this larger blue box, right? So what we don't want to do is to actually control the end effect, the joint angles. Instead, what we're suggesting is to control the end effector relative to the target box. And then what of course happens in the real world is that typically when the box is picked up, it's in like some kind of awkward maybe pose relative to the end effector because of, uncertainty. But that doesn't really matter in our approach, where we propose to reformulate the optimization problems to optimize for relative Cartesian frames. Because now that we have this object in the hand in whatever pose relative to the end effector, we switch to controlling the green box relative to the target box. And so this position of relative to the end effector doesn't matter if this is what we're controlling for. Okay, so essentially we take this overall idea of combining a symbolic solver with a trajectory optimizer and move it from optimizing over an augmented joint state to an optimization over relative Cartesian frames. So now you see, if you compare these two solutions, that we are optimizing not over joint angles anymore, but over relative Cartesian poses. And therefore, this decouples the constraints over time, which is much easier to formulate. And you see that now the objective becomes more potentially more complex because this one is now over the entire trajectory, right? The plan, however, stays valid even if the object moves, right? Because if you move, for example, now the blue box in this particular problem, you still have a valid plan of actually, you want to align the green box with the blue box in a particular way, right? So at the lowest level, once we have all these optimized relative Cartesian frames, we really just use an operational space controller to minimize this distance, for example, between the green box and the blue box, wherever they are actually in the world. So as a resulting system then basically looks like this. We have a planning box that essentially searches for a symbolic plan and then checks if a Cartesian plan or a sequence of relative Cartesian frames can actually be generated. So this is done in the planning box. Then this optimal frame skeleton is basically sent to the execution, and there we essentially output a trajectory and give this trajectory to the reactive controller that then basically interacts with the environment at a very high bandwidth. So we can basically react to any movements of these objects, but we cannot yet really change maybe the relative poses of the Cartesian frames online, and we can also not yet change the symbolic plan. So this would be a very interesting future work to automatically essentially detect the case when you would actually want to adjust to this. But overall, here's the system or a result of the system and what it can achieve. So this is the Tower of Hanoi problem. And because we're using a symbolic planner, we can basically solve these long horizon tasks that require really planning over many time steps. And we can also find multiple solutions, in this case, 2 of them. And I've already shown you this result, that even if the objects move, the plan actually stays valid and the robot can still execute those. And of course, I always like to see robots moving in the real world. So here we took our visual tracker that I showed you in the beginning. And we are basically executing a plan and an optimized sequence of Cartesian frames in the real world. And you see Toki actually being, again, like very annoying to this robot, so that it has to react and adapt its motion to the dynamic environment. But yeah, no matter how Toki changes it, the robot can still finish the task. So just to summarize this work, which, by the way, was presented at ICRA this year, you can still go to the Slack channel if you want to ask any question. But to summarize this, the title of this work is Object-Centric Task and Motion Planning in Dynamic Environments. And the main idea that we put forward here is that we optimize relative Cartesian frames. And the algorithmic contribution of this work is that we then had to reformulate the entire trajectory optimization problem to be able to do that. But it results in a task and motion planning algorithm that works in dynamic environments. Up till now, I have talked a lot about perception and action in manipulation tasks, and I showed you a real-time tracker that can actually track 60 object poses despite large occlusions and model uncertainty. And I've also shown you high-level task execution, but I haven't shown you any learning yet. All of these methods were actually completely model-based, And if you have these models, you should really use them because it works super well. But of course, not everything can be modeled, and learning has its place also in robotic manipulation. So I haven't had time during this talk to talk much about it. So I wanted to just conclude to show you, okay, I presented you with a system that combines real-time perception methods with reactive motion generation methods. And I also showed you how similar ideas can then be even extended to also include a task and motion planner for planning even longer horizon symbolic tasks. And decision-making for manipulation really requires real-time perception and reactive motion planning. That is something that I think you should be taking home after this talk. But I also want to make a quick plug here, since I mentioned that none of these works actually uses any learning. I use a lot of learning methods also in my work for manipulation. And one example is, again, a method that actually won the New Scenes Tracking Challenge at NeurIPS in 2019. And what we have done here in an autonomous driving setup is really just to use a vanilla Kalman filter just in the way you would think you would want to use it, based on top of a learned object detection method. And we've done very well. At this point, we have actually been outperformed, as I recently saw. So I'm excited to actually check how we can advance here. But yeah, I just wanted to emphasize basically why we have used a modeled, like a model-based observation model in the object tracker. I can also see a method where we use basically a learned object detector as a virtual sensor in a Kalman filter and achieve very good results. So thank you very much for your attention. I would like to thank my students who are doing amazing work and all my funding sources. Thank you.